Let's take a look at a completely different LED tester. This is the HWL300. It seems to be an established unit, and it looks as though it may be a lot safer than that previous abomination I looked at that was basically referenced to mains voltage. So I'll get the box out the way. You get a choice of plug. This came from AliExpress. It cost about £10, I think it was. £6 unit and a bit more for postage. And it comes with two test probes. The test probes have the usual arrangement of the little bung up the end. We'll whip that out and get rid of that. The bits that we'll lose immediately because they're never going to be put back in. And it also has the protectors in the front, which are quite good to keep on because these are very sharp probes. The feel of the leads is also pretty good. Let's plug it in and test it with some LEDs. I've already tried this. I've done some tests. The open circuit voltage is disturbingly high. It goes up to, the output is, it says 300 volts, and the current it tests the LEDs with is 20 milliamps. Even if it's a huge high voltage filament like this. Let's put this to the test. I shall bring in my little electrical test box here with its convenient plug. I shall make sure the probes are in a safe place. I shall turn it on. It immediately displays 306 volts. Let's actually test the voltage. Let's get the meter onto this. So I shall set this to 1000 volts DC, and we'll stick the probes on and see what it reads. And see if it changes the other reading, because there may be an impedance thing involved here. 300 volts. Okay, well, to be fair, that's dead bang on for the data, but it is showing 6 volts too high on the display. That's all right. Let's test it on some LEDs. Let's also get these things out the way here. So we'll start with a conventional LED, and the reason for the LED display in this is it shows you the voltage. So make sure you get the correct polarity, because this is putting out quite high voltage. You put it on, and the LED ramps up and it shows 2 volts. That seems a bit too low for a blue LED. Okay, what about this red LED? If I put it on, it's got a higher voltage, 4.8. I'd say that starts going about 5, so it's still a wee bit low on the voltage indication. On these, we've got 10 chips in series with 10 sets in parallel, which is going to be around 27 volts-ish. 25 volt, it's reading a bit low. And then we've got this mofo of a LED filament. So I'm going to stick it on here. And once again, it just gently ramps up. That is bright. 275 volts across that. Interesting. I like the way that initially when you connect it, I'll turn it off now. Initially when you connect it, it seems to start with an open circuit high voltage, but then it immediately drops and then it starts ramping the current up. Right, let's open this unit. So I shall unplug it. I've already turned it off. We'll get this power supply out the way and we'll pop the lid off it. Quite a useful device. It does come with a warning. It says if it's low voltage LEDs, make sure you get the polarity right or test with low voltage first. That's because this would nuke an LED with that slight high voltage pulse if you connected it initially. Most likely. What screws are these? Oh, they are crosshead. They're fairly close to the end. Where's my other screwdriver? Is this going to work? Yes, it is. Let's take a look inside and see, is it properly isolated? And what's the circuitry like? Here we go. Oh, fairly complicated. What am I seeing here? Well, what we're seeing, I shall zoom down this, is a switchboard power supply with an opto-isolator and a class Y capacitor that suggests the output is isolated. There's the LED display. That chip there is probably the display chip. Is there a little microcontroller controlling this? This is fairly complicated circuitry here. Interesting. Right, okay. I'm getting deja vu here. As if I've seen this before. One moment, please. Not identical, but very, very similar. This one is the Geston model DLV300 Super LED tester, which also says 0 to 300 volts, universal input voltage. I wonder if they're from the same company and they've evolved over time. Anyway, I shall whip the circuit board out and we shall explore this. One moment, please. Reverse engineering is now complete, and that's an understatement. It took me 3 evenings to actually reverse engineer this because there are so many complicated sections and it's got some very ingenious design in it. In that time, I made 2 complete other videos just as a break from reverse engineering this. It was complex. So let's explore. I'll zoom down just a little tiny bit so we can see the circuit board closer up. The power supply is based on a lamp driver chip being used as a power supply. It's a BP9022A, but they're cheating. They're using it in a very unusual way with an opto-isolator and a 431, TL431 style chip as a voltage reference to generate a nice stable 300 volt supply on this death beam capacitor. The soft start that we saw of the LEDs fading up is done entirely by this MOSFET and this capacitor being charged. It's quite ingenious. There is a LED driver chip, another one, but this is a current regulating, basically a buck converter based on an inductor here. And that provides current limiting, but at 2 thresholds. It can actually supply 20 milliamps and 50 milliamps. I didn't know this until I reverse engineered it and saw that, and then worked out how to do it. It's done with this opto-isolator and this MOSFET switching a current sent resistor. There is a 18 volt Zener diode down here with a transistor, and I didn't know what that was for, but I remembered in the instructions it said something about use the 18 or 90 volt mode, but I didn't know what they meant by that. And it turns out there is a mode because if this transistor is enabled, this Zener diode will cap the voltage at about 18 or 19 volts. We'll explore that later. We'll try that. We'll see if we can find out how to unlock that feature. After that, there is the microcontroller with its own little 3.3 volt regulator. It's driving the display, but I thought this was just a dumb LED display chip, but it's not. It is actually controlling other functions in this. It's very complex. Let me show you the back of the circuit board. It's mirrored, so you can have a rough go at reverse engineering. I wouldn't totally recommend that because there's so many hidden tracks. So many hidden tracks that at one point in reverse engineering, I had to remove large components just to see what was under them. It turned out there's nothing under them, nothing of significance. This was of significance. It was the only way I could really get progress in reverse engineering this. Very complex. Right, let's take a look at the schematics, because there are lots of schematics. I had to break it down into 4 different sections. It would not fit in one page. This is why it took so long. Let's start at the very beginning. It's a very good place to start. We have fuse 1. The fuse is 1 amp. And there's a switch on the neutral. That's a bit naughty, but that's okay. There's a bridge rectifier, and then there's a 10 microfarad death beam capacitor here, and that provides a stable, roughly about, say, in the UK, it'll be 340 volts, say, DC supply. This chip is not meant to be used the way it's being used. It is a LED driver, current regulating LED driver. You set the current with the current sent resistor, and it would normally, the output would be diode, smooth capacitor, and then your LEDs, and that would be it. But because they're using it as a regulated supply, what they've actually done is they have the current sent resistor as normal for regulating the current that can go through. But they also have the overvoltage protect. You'd normally just have 1 resistor to ground for that, I think, to ground. That would set a threshold that if the LEDs went open circuit, it would basically turn the chip off. They're cheating that. They're using an opto-isolator to switch a 5k resistor in up to the positive rail, and that basically turns a chip off when the voltage reaches the prescribed level at this side. I shall explain that in a moment. So the supply on this side, the VCC supply, is a resistor. It'd be nice to have two of those in series, and a capacitor, and then they're just using that opto-isolator to cheat that. Very interesting. Only have a snubber network because they're professionals. They knew what they were doing and they did it properly. On the output side, we have two US1M diodes. I think, can't really test that now because I've boxed it all back up. I think they're standard silicon diodes, but high frequency. They got fast recovery, which means they're basically more robust than a Schottky diode, which is probably why they've used them. So they got two in series, even though they are rated 1000 volts each, just because they were playing safe. And they've got another 10 microfarad, 10 microfarad, 400 volt death beam capacitor. Then on this side, they're generating, because they're using a TL431 voltage reference chip. This is basically, it's a little 3-pin chip, really common. It's used everywhere. And it's got a threshold that on the input, if it reaches 2.5 volts, it will start basically turning on. It's a very precise voltage shunt. And if you just tied that to positive rail, it would just shunt at 2.5 volts. But if you use a voltage divider on the input, it will actually allow you to program that. So because this chip isn't rated for super duper high voltage, they've got a 620k resistor again, and a 12 volt Zener diode, providing roughly 12 volts to the LED of the opto-isolator, and then the shunt regulator. Then they've got a divider here, 620k, 620k, again, they're really using standard values, and then their favourite value of resistor of all, 10k, and that forms a divider so that as this reaches just over 300 volts, this reaches 2.5 volts, little stability circuitry, a bit filtering circuitry, it turns the LED on, LED lights the opto-isolator, opto-isolator tells it, oh no, overvoltage protect, and the chip turns off. When the voltage goes down again, the opto-isolator turns off and it says, oh, everything's fine, and it starts again. It's ridiculously clever. Oh, and the little class Y capacitor down here as the suppression filter because they're professionals and it's a proper capacitor. This unit cost the same as that complete death trap I looked at not that long ago. Basically that you were just holding leads that were connected directly to the mains and it could have killed you. This one is isolated and it is just the same price, and it's so sophisticated. It can do so much better for the LEDs, but more importantly, much better for you. Here is the current control. So this is a, oh, hold on, what is that? It is a DU8613 chip. It's worth mentioning that they've got a capacitor connected to one of the pins that is not actually used in this chip, so I'm not sure what's going on there. Maybe it's a drop-in chip for some other application, but this capacitor is connected to a supposedly unconnected pin. So we get a power supply for this chip based on two 360k resistors and a capacitor, and that provides VCC. That's the sort of positive voltage for this chip. We've got a 100 ohm resistor from that also for gate. That's for a little extra MOSFET inside, just an extra auxiliary function. There's two MOSFETs in series inside it, and that turns this one on. I don't know what function it serves. It's probably some special purpose. After that, it's a conventional buck regulator with a little inductor, the freewheel diode, and the capacitor, quite a low value, 22 nanofarad, 630 volt super death beam capacitor. And normally, it would normally just have LEDs between here and here. This is the 300 volt supply, and this is the regulated 0 volts. I'm having to call it the LED 0 volts because it's not the actual 0 volts, the rest of the circuitry. It's complex. There is another current sensor resistor, 6.8 ohm, that can be turned on by this MOSFET, which is driven by this opto-isolator, which is driven by this LED, which is controlled by the microcontroller. I could have turned that upside down. The LED 0 volt would have been up there, but that doesn't matter. Anyway, when the microcontroller says, turn the current up, I didn't know about this feature either. It turns this LED on, and it turns the opto-isolator on, and it brings a 6.8 ohm resistor into parallel with this existing current sensor resistor, and it goes up from 20 milliamps to 50 milliamps. I've tested that. It works. I'll show you afterwards. There is another thing common to this LED 0 volt reference. The power supply transformer has 2 windings. Let me just dig through this here and show you the 2 windings. It's got the primary there, it's got the 300 volt winding, and it's got an auxiliary winding that produces over 3.3 volts. In this case, it actually produces 9 volts. That 9 volts goes through another of their favourite diodes to a 680 microfarad 25 volt capacitor, and it provides 9 volts to the logic section that then gets regulated down to 3.3 volts. Sorry if this is boring. It will only appeal to a very small minority of people, I'm afraid. This is why the dumb take it apart videos are more popular than my super duper over complex ones, even though mine involve a lot more work. Moan, moan, moan. Here's where it gets wild, as if it wasn't complex before. This bit is it's bending my mind. This MOSFET, which is a discontinued MOSFET, but that doesn't deter the Chinese who clone it to death. It's at FU1N60A. And this MOSFET is an N-channel MOSFET, which means it's normally used to switch down to the negative rail, but in this case it's tied up to the positive rail. And there's this capacitor. I measured it in circuit. There'll be other influencing factors, but it measured about 7.4 microfarad. And this circuit, normally there's not a lot of current flowing through when you first connect the leads. It's just enough to basically detect that something's connected. And what actually happens is that when you actually connect a load across it, the voltage here drops down. It goes away from the 300 volt supply, and this generates a 12 volt supply via these resistors, and then it trickle charges this capacitor on the gate via this high value 1.2 mega ohm resistor. And what that results in is, as the voltage in the gate rises, the LEDs dim up. This is the bit that dims the LEDs up once you actually connect a load. There is a diode here, which I think is a reset. When you take the load off, I think the voltage that is accumulated on the gate here will basically go boom to the 300 volt rail and give a quick reset. Then it goes via one of their favourite diodes, lots of favourite diodes, and then it would normally go to the regulated supply here, and it would go through the LEDs, right? But a couple of things here. There is a divider from the output to the LEDs, 2 620k resistors and a 10k resistor going to the microcontroller voltage sense, which has a little decoupling capacitor next to the microcontroller. The microcontroller can also send a signal to this pin here and turn on this very standard transistor, and when it does, it shunts an 18 volt Zener diode across the LED output, capping the voltage to 18 volts. We have to work out what enables that feature. I don't know what enables that feature. I tried tapping the lead scare, nothing happened. We'll experiment. Next bit of the circuitry is the microcontroller itself. It's the simplest bit, except the software isn't really the simplest bit. It has a programming port. It is the 9 volts come in, 3.3 volt regulator, decoupling capacitor, 3.3 volts goes to the microcontroller. It's got the display with 3 digit drive lines, and then 8 330 ohm resistors as 2 little 4 resistor packages for the segments. Then it's got the voltage sense input that I showed you earlier via this little decoupling capacitor, so it can actually display the voltage. Nudging those resistors, fine tuning them, is the bit that will make that accurate. There's the output to the 19 volt enable, and there's the output to the bit that switches between 20 and 50 milliamps. Okay, I can show you the 20 to 50 milliamp switching bit because I've worked that out. See, that was 3 nights work. That's how long it took to describe it. It took longer than usual. That's fine. Where is the unit? What have I done with it? That is not the unit I was looking for. 1 moment, please. I'm going to have to find the unit. I have found the unit. Let's do some tests. Now I'm more confident because unlike the other unit, this is actually isolated from the mains, although it does still have 300 volts across the output and could give you a little zing. So this is shot up to 306 volts. As before, when you connect it to the LED, it ramps up. But watch this. After you've held it on for approximately 10 seconds, it will step the current up to, from 20 milliamps at the moment, it'll suddenly step up to 50 milliamps. It's just done it. And the voltage across the LEDs rose accordingly. But it won't do it with lower voltage LEDs. Say, for instance, this one. I don't know what the voltage threshold is. I will hold it on here. So this is just passing 20 milliamps through this LED. It's showing about 7.3 volts, not quite accurate, but good enough for a rough indication. Now, is this going to step the intensity up? I only think it happens with the higher voltage LEDs because it knows that they're probably rated for higher current. Now, nothing has happened. Okay, that's fine. I thought maybe you'd tap the leads together to get the 0 volts. What if I hold it in 0 volts? Anything? It's flashing. 18 volts. So that's not going to like this. That is how you unlock that mode. So that should like this LED, but it is just capped at 18 volts now. Can you go back the way? What happens if you hold it again? It's flashing again. And it's gone back to the 300 volts. What happens if you hold it even longer? Does it just burst into flames? I'm surprised that that regulator chip can basically regulate continually. Anything going to happen? I wonder if you held it long enough, would it go into calibration mode? Maybe that's not ideal. Or maybe it is. No, I think that's it. It's capped at the 18 volts again. Okay, so that's how you activate and deactivate the mode. You just, basically, if you watch the display there, when I hold the leads together, it displays 0, and only when it's displaying 0, and it flashes the bars, and then it goes between the two voltage ranges. That's very clever. I don't remember anything about that instructions other than mentioning it. So if you've got one of these, it's got a special mode. Just short the leads together briefly until it starts flashing the display, and then it goes to other mode. And also, just in case you didn't know, you've got that other function that if you're testing LEDs and you do hold it on, then after about 10 seconds, it does suddenly increase in intensity. I don't know if you'll even see that on this. If I hold my hand like that, will you see it when it suddenly goes whoop up to the higher intensity? It suddenly went up to the higher intensity. That's 50 milliamps. Righty-ho. That was a very worthy and interesting but also frustrating teardown. It turns out that this is a very sophisticated unit, and now I'm thinking about it, this older version actually may have less features, because it didn't have the opto-isolator, so it may not have that current increasing. It may just be that this is a new evolved version, the HWL versus the DLV300. This one has added more features. But there we go. Interesting. Very interesting indeed. Now I'm going to experiment that other unit, and if it's got anything special, I'll leave a note down in the description. But in the meantime, this is the HWL300 Super LED tester. Much safer than the other crap that I looked at before, and it's got lots of hidden features that I didn't know about, and very, very clever circuitry. It's very neat indeed.